In this video, I will give you a quick introduction to the concept of pressure. By definition, pressure, the left side here, this is pressure, is defined as the fraction with the numerator having the force and the denominator of that fraction is the area. Now, in most cases, even though we know force is a vector, area is a number, we can divide a vector by a number, and that means pressure is also a vector. In most cases, though, we don't really care much about the direction of the pressure vector. The most important quantity that we need most of the times is the magnitude of the pressure. And to find that, we just need to use the magnitude of the force over the area. Now, one simple example would be if you have a force, say 5 newtons, and this force is applied, let's say we have an area of 0.50 meters squared. If you apply a force of 5 newtons in this much area, then you would be getting a pressure that is 10 newtons per meter squared. Now we don't, it is okay to use newtons per meter squared, and you get those units by saying in the numerator you have newtons, in the denominator you have meters squared. So the units of pressure will be newtons per meter squared. You can also say that that is 10 pascals. Okay, 1 pascal is the same as a newton per meter squared. Now I want to mention in kinematics and in Newton's second law and then in energy. So at the beginning of the semester, we have been using the concept of force quite a lot, both to find work and to predict how objects move. When we work with fluids, though, we don't use much force. We use more often we use the concept of pressure. So when you work with fluids, it is more useful to know how much pressure you have, how much pressure the fluid applies on the surroundings. And pressure involves knowing both the force and the area. Both of these concepts are important when we work with fluids. Now, pressure is also useful in other cases, and I can show you an example. When we have, let's say, I have this is a pin. And of course, what we do, and let's say this is a wall or a table, whatever, some kind of surface where you want to drive the pin in. When we have our finger, okay, this is us, and we're pushing on the pin downwards. If we say for now that the pin is not moving, it's stationary, the acceleration of the pin is 0, you can use Newton's second law to show that the force that the pin exerts on your hand is the same in magnitude with the force that the pin exerts on the surface. So the force that you have upwards, the contact force from the pin on you, and the contact force that the pin exerts on the surface, You can use Newton's second law and Newton's third law to show that these two are the same in magnitude. Now, the forces are the same, but there is a big difference in the area. Here you have a large area, and here you have a tiny area. Now, because we have a large area, that means that the pressure is small on the hand from the pin. Now, on the other side, if you look here, we have a tiny area because the tip of the pin is so tiny. The diameter of this is so tiny. So the fact that we have a very small area means that at this point in the interface between the pin and the surface, you have a very large pressure. And the effect of this very large pressure is that you're able to have the pin going into the surface that you want, whatever that may be. So there are cases where the concept of pressure is useful, even if those cases do not involve fluids. But it is true though, when you work with gases or when you work with liquids, both of these are examples of fluids. We do use pressure the vast majority of the time. We don't really think in terms of force. With fluids, we will be using pressure, and a lot of the theory that you will see in this material with fluids will be about pressure.